Okay, I've got the signal. Time to begin. Today we finally get up to what we've been striving for the last couple of lectures, and that's to talk about the trigonometric functions. And so remember that we talked about the trig ratios, and that was to do with triangles. And then we extended the idea of the trig ratios so that we could get values for any angle, positive or negative. And so the idea today is that we're going to draw a graph of the trig ratios for any angle now that we know how to do it. And I've got a little picture here. It's a nice little picture. Remember our definition of the sine and cosine of an angle. So if I've got an angle like 45 degrees there, then the cosine of 45 degrees we've said is the x-coordinate of the point P. So the sine of 45 degrees is 0.707 approximately. That's 1 on the square root of 2. Likewise, the y-coordinate is the sine of that angle. But for the minute I'll just go with the x-coordinate. So I'm just working with the cosine of this particular angle. So let me go back to 0. So when theta is 0, the angle that the radii makes with the positive x-axis, of course, is just the positive x-axis. And so the x-coordinate is 1, so the cosine of 0 is 1. Now let me move theta, so this goes around, and I'm going to plot the x value, the x-coordinate, for each angle. So here we go. As we move along, as you can see here, there's the x-coordinate 0.95. There it is plotted. So when the angle is 18, the cos of 18 is 0.951. And as I move around, this is the graph that I get. So for each angle, it's worked out the cosine. Now, here we're in the second quadrant. The x-coordinate is negative, so our graph is negative. And around we go, and there it is. And of course, as this goes around the circle more and more, that just repeats. Likewise, if I were to go the other direction, it would repeat in the other direction as well. And so that is a graph of my function here. And the important thing about that graph is that it passes the vertical line test. So this is definitely the graph of a function. Okay? Now, unfortunately, this picture here had everything nicely in degrees. Convention has it, and as I said later on in calculus, it's an imperative thing, that we actually measure along here not degrees, but radians. So really the ticks along here should be 0, pi on 2, pi, 3 pi on 2, and up here 2 pi, and so on. Okay? So our angles for our functions we are going to measure in radians. Okay, so that's where these graphs come from. This is our trigonometric functions. So, armed with that, let's move on. So, there's the picture I just drew. That's the graph of function x is equal to cos x. And as I said before, it didn't matter when we were talking about triangles whether we use bracket notation or not. But now that I'm talking about a function, I think it makes sense to use function notation for your sine, cosine and tans and so forth. You don't have to. It's not wrong if you don't. I'm just saying to you, I think it's a good idea. This we are thinking of as a function. And as you can see here, I have the x-axis in radians, pi on 2 pi, 3 pi on 2, 2 pi, etc. So this thing is very definitely a function. It passes the vertical line test. And the domain of that function, for what values of x can I calculate the value of cos x? And the answer is I can now do that for any real number whatsoever. Okay, just go around that unit circle, find the appropriate x-coordinate. So the domain is the set of all real numbers. What sort of numbers do I get when I do this plot? You can see it here. I only get numbers between -1 and +1. So the range is the set of y values such that y is between -1 and 1. That will be the range. And I think, hopefully, you understood that this goes on indefinitely in both directions. So this is our final class of functions that we're talking about. So essentially we've got polynomials, we've got exponentials, we've got logarithms, and we've got trigonometric functions. They are the basis of all of our scientific and engineering mathematics. You can do so much with those that will keep you busy for many years. Okay? With these functions, we saw with exponentials, we saw with logarithms and so forth that we had special properties. Those particular numbers had special properties. Of course, so do these ones. We've seen the trig identities, but there are some other things that are obvious, I think, from this graph. One of them is this. If I chose a particular x value, it doesn't matter. Let me choose this one here. If I chose a particular x value, and I've just chosen enough, if I go 2 pi further units up, which puts me to here, because the graph repeats, that value will be exactly the same there. So if I choose x and x plus 2 pi, the function value should be the same at x as it is at function x plus 2 pi. Okay? Just because this graph repeats, and that graph repeats because we're just going round and round and round the circle. So, over the page here, it says, for this particular function, function x plus 2 pi is equal to function x. That's what I just said. And the language that goes with that, we say the function is periodic, i.e. it repeats, and it repeats every 2 pi units. So the mathematician would say the function is periodic with period 2 pi. So let me highlight this because this is an important property. As I say, that's why we use the trig functions, because it's periodic. We use them to model periodic phenomena. Now the other thing, I'll bring this back, it's not immediately obvious from the portion of the graph that I have drawn here, but if I were to draw more of this, so it came down like that and went around, you would believe, I think it's reasonable, that this graph is symmetric about the y-axis. All right, I think that seems obvious from the picture. And mathematically, we know that something that is symmetric about the y-axis is an even function. And algebraically, that says function minus x is equal to function x. So this function is even. And if I were to do a picture here, look, here's x, minus x is just as on the other side here. So there's minus x sitting there. And so once again, it's got the same function value. Because it's symmetric, if I go that far on that side or that far on that side, I'll end up with the same function value. So they are two important properties of the cosine function. The function is periodic with period 2 pi, and the function is even. Now, to produce the graph of cos x, what I did was, as the angle went round the unit circle, I plotted the x-coordinate of point P. If I plot the y-coordinate instead, then I get the graph of sin x. So here's the graph of sin x obtained in exactly the same way. As you can see, it has a similar shape, but it's not quite in the same position. So the domain, again, for what values can I calculate sine x? Well, the domain, again, is all real numbers. I can calculate sine x no matter what value of x you give me. And the range is the same as our cosine. The range is the set of y values between -1 and 1. There's only, for every point on the graph, its y value is somewhere between -1 and 1, is what that says. And so that's our, excuse me, that's our sine graph. And for the sine function, once again, it's periodic with period 2 pi. It repeats every 2 pi units, because once you go around the circle, the y coordinate's back to where it was before. So it's periodic with period 2 pi. But in this case, if I were to extend this graph down here, it's no longer symmetric about the y-axis. If I did that reflection there, that hump would be up the top. Right? So it's not a reflection about the y-axis. What it actually is in this case is, had I drawn a good picture, if I turn that upside down, it looks the same, is the idea. And so this thing is, we say it's symmetric about the origin, and we had a term for that before. We said the function was odd, i.e. function minus x is minus function x. So let's pick the same point as we did before. So if here is x, up to there, that's function x, minus x is just over here, and down there, that is function minus x, and you can see function minus x is the negative of function x, which is what we've got here. So our function, our sine function, is odd. The cosine function is even, the sine function is odd. I would say to you that you should know what the graphs of sine and cos look like. Your cheat sheet's getting mighty full, but I'd have the graphs actually sitting on there. Seems like a sensible thing to do. That way you don't get it wrong. Now, if I can, just let me jump over the page and then I'll come back to this statement here. So, over the page, I've drawn the graph of cos x and sin x on the one picture. Here it is. So this one, the dotted one, is cos x, the solid one is sin x, and I think it's reasonably clear in here that to get the sine graph from the cos graph, all I have to do is just shift it right by pi on 2 units. Agreed? The sine graph is the graph of cos x shifted to the right by pi on 2. So that seems reasonably obvious from the picture there. We can express that algebraically, and we had done some of this week 3, perhaps. I don't know if you can remember, but if I've got the graph of a function, cos x, so if I have the graph of function x, then I know the graph of function x plus k moves the graph to the left by k units. So here, I've gone, I want to move to the right by pi on 2. So the sine graph is the cos graph moved to the right by pi on 2 units. So that's the algebraic way of saying the graph's shifted across. Now, interestingly, actually you might not find it interesting, I find it interesting that cos x is, if I can just slide up here, cos x is even. So function x and function minus x are exactly the same. So in here I could have written this. If I multiply this by minus in here, I'll get the same result. So this is the same as cos of pi on 2 minus x. All right, so sine x is also cos pi on 2 minus x. And of course that agrees with our, way back here in our triangle, we said the sine of theta was a over c. The other angle in here we said was 90 minus theta, pi on 2 minus x, and of course that's the cos of 90 minus theta, a over c. So the sine of theta is the same as the cos of 90 minus theta. So that's what we've got right here. So that trig identity is reflected in our graphs, in fact. So I told you it was interesting. Okay. So what I'm actually doing here is I'm going through and I'm showing you a lot of the properties of the sine and of the trig graphs. You'll see these and believe them to start with. It may take you some time to become familiar with them. Okay? The more you work on exercises and so forth, the better you'll become at actually working with each of these properties. Okay, so finally the tan graph. To get the graph of tan x, we use the fact that our definition now of tan x is sine x on cos x. And so, what I do is I get the value, for a particular value of x, I get the sine value, I get the cos value, and I divide those two things. And in here, it seems therefore that I cannot calculate the tan of x whenever the cos of x is 0. So in here, so tan x will be undefined when cos x is equal to 0. If you have a look at the cos graph, you can see that it's 0 at pi on 2, 3 pi on 2. The next one will be 5 pi on 2, and so forth. Okay? So wherever cos x is 0, tan won't be defined. And so sitting in here, pi on 2, in fact, will be a vertical asymptote down there for the tan graph, as will be 3 pi on 2. So we have vertical asymptotes in the graph of tan x. And so I can say the domain of the tan graph, the domain. Now, essentially, I'd probably be happy if you said the domain is all the values of x except where cos x is 0. But we can write that in a fancy way. I can say it's the set of x values such that x is not equal to plus or minus 2k plus 1 times pi on 2, where k is an integer. So what this is trying to say is it's any odd multiple of pi on 2. So 1 pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2, and so forth. So it's the odd multiples of pi on 2 where tan x is not defined. But as I say, if you understand tan x is not defined where cos x is 0, that's good enough, I would say. And sitting in here, because cos x gets really, really, really small, dividing any number by something really, really small gets you something really, really big. And so our tan graph, in fact, gets all values in its range. So the range of the tan graph, the range is the set of all real numbers sitting in there. So the tan graph's a little bit different in nature to the sine graph and the cos graph. So that's the graph of tan. The other thing here before I turn the page is take a look, and you can see the tan graph is 0 at 0, it's 0 at pi, it's 0 at 2 pi, and it seems, therefore, that this graph repeats itself not every 2 pi units, but every pi units. So this graph is periodic with period pi, rather than 2 pi. And so we can say for tan x, the graph is periodic with period pi. And the other thing here is I've said, look, the function turns out to be odd. And once again, if I were to turn that upside down, it looks the same. That's our property of a odd function. So the tan graph is periodic with period pi, and it is odd.